Climbing robots can investigate exposed strata on steep terrain features that conventional rovers cannot access, such as cliff faces in Martian craters or subsurface lava tubes on the Moon and Mars. These robots often use arrays of small hooks called microspines that can catch on small-scale surface features of the rock face. To produce adhesion, microspines must be loaded tangentially to the surface, either by actuation or gravity. Robots with actuated grippers can produce a large internal preload and support forces in any direction, but at the cost of increased mass and grasping time. In contrast, passive grippers are smaller and lighter, but these robots are typically restricted to simple terrain such as flat walls or poles. Palmer et al. Introduced the concept of directed inward grasping, where preload forces are generated between opposing feet rather than within each gripper. This combines the benefits of both active and passive approaches, but still requires a gripper capable of supporting a varying loading direction over the course of its step. In this work, we present LORIS, a lightweight observation robot for irregular slopes. LORIS uses a novel splayed gripper design and force optimization strategy to produce directed inward grasping forces. Both the gripper and wrist joint are passive to reduce actuator mass. 3 degree of freedom legs enable LORIS to traverse irregular terrain features, and a spine joint can assist with corner transitions. A long tail helps prevent the robot from pitching backward while climbing, reducing the adhesion force that the grippers need to provide. LORIS can operate untethered with an onboard computer and battery, and a RealSense depth camera is used to map the terrain. In future work, this map will be used to autonomously select footholds. We'll start by discussing the design of LORIS's grippers. Actuated grippers, as shown here, have a full ring of microspine carriages that are collectively pulled inward to generate preload force. Because of this symmetric shape, there will always be spines oriented to oppose forces pulling from any direction. By the same token, such a design cannot be made fully passive because there is no direction that the gripper can be unloaded to disengage the spines. We instead propose a splayed gripper design with 2 carriages spaced 90 degrees apart. External loads are naturally distributed between the carriages, enabling the gripper to support loads over a range of angles, but the gripper can still be unloaded upward to disengage from the surface. We use a static analysis of the gripper to compare different variations of the splayed design, including different numbers of carriages and angular spacings. The external load produces some displacement of the gripper, which then generates a load at the spines. We can compute the feasible cones of external load and displacement such that all spines are positively loaded, otherwise those spines will disengage. The results of this analysis show that 2 carriage designs outperform all other variants, and the maximum loading angle increases linearly with the angle of the outermost carriages. At carriage angles beyond 45 degrees, the spines can no longer effectively catch on the surface. The selected design, shown on the left, can nominally resist loads up to 45 degrees, although a more conservative 30-degree limit is assumed in practice. A second important consideration is the placement of the passive wrist joint. Using a similar analysis, we show that the optimal pivot location lies along a line passing through the spine tips. If the pivot is too close to the wall, then the gripper will pitch upwards, causing the spines to lose purchase. If the pivot is too far away, then the induced moment will pry the spines free of the wall. Next, we discuss the strategy LORIS uses to allocate contact forces between its grippers. We define an optimization problem for the adhesion margin, C, which represents the minimum normal force needed to dislodge a gripper. The contact forces are subject to several constraints. We make a quasi-static assumption, so the forces must be in static equilibrium. As in prior literature, microspines are subject to constraints on their minimum and maximum tangential load, as well as the out-of-plane loading angle, phi. We additionally add a constraint on the in-plane loading angle, theta, using the value we derived earlier for our splayed gripper design. The tail is assumed to slide along the surface, providing only a positive normal force. We can solve this optimization problem as a linear program in real time to continually optimize the robot's force distribution. We can examine representative solutions to see the effect of the splayed grippers on the optimal contact forces. The robot is shown taking a step with the front left foot using conventional passive grippers that cannot produce lateral force components. In contrast, when equipped with splayed grippers, the robot is able to produce a much higher adhesion margin by generating directed inward forces between the grippers. These forces arise naturally from the optimization, allowing them to update automatically as the robot's posture changes on more complex surfaces. We see that LORIS is able to ascend several different substrates, including cinder block, vesicular basalt, slag, and tufa. All of these trials were conducted on vertical terrain and full Earth gravity and shown at 8x speed. Results are shown for sets of 10 trials on each surface. 2 sets of trials were conducted on cinder block with and without the directed inward grasping forces. We see that these forces lead to a significant improvement in the robot's reliability. In conclusion, we propose the use of passive grippers and wrist joints to reduce actuator mass, enabling a wider range of mission profiles. While conventional passive grippers are limited to flat surfaces, we can use splayed grippers to climb on irregular natural terrain. Our contact force optimization approach takes advantage of these grippers to generate directed inward grasping forces, which have been experimentally shown to improve climbing reliability. One direction for future work is on optimal foothold selection to enable autonomy and improve climbing reliability further. Another area of research is on dynamic motions such as leaping or fall recovery, which are enabled by the much shorter grasping times of passive grippers. Thank you for listening.